Hello, my name is Sanna Patil, and me and my team members have decided to work on resonance fluorescence as a topic for our PS530 project. So, first of all, what is resonance fluorescence? Resonance fluorescence is uh, is a phenomenon in which an atom absorbs a photon and at some frequency and then re-emits it at that same frequency. So there are two types of resonance fluorescence. One is the coherent uh, one. The coherent one is just the radio scattering of photons, and the incoherent one is the spontaneous emission of photon due to decay of excited state into ground state. Here we will look into one of the phenomena of resonance fluorescence. In total, in this paper, we will look at three of the phenomena. So the first one which I want to talk about and which is given in the paper is that the phenomenon where a two-level emitter, a two-level emitter is just the atom with one excited state and a ground state, under weak monochromate excitation, which is usually by a laser, scatters out photons that are antiquons and yet exhibits the driving laser's line with it. So, while both phenomena can be calculated by unwavering formalization of light atom interaction, but their interpretations are not very clear. So, if we see anti-bunching is interpreted in the single photon picture, where TLE absorbs and re-emits photons one at a time. However, this picture fails to account for RF line width, which is far narrower than the natural coordinate, which is 1 by 2 pi T1, where T1 is centimeters radiative timeline, lifeline. Yeah, so it's way narrower than that. So how can we explain this RF line width with also the photon anti-energy? For that, we would look at the broadband component of the RF spectrum as shown by Lopez Carano, theoretically that the broadband component, even if it is insignificant at under weak excitation, holds the key to the presence or disappearance of anti-bunching. But okay, so drastically departing from single photon picture, the boson component was attributed to higher order scattering, which is the actual two photon absorption and emission. Now the problem with this is we have the result is spectral resolution. Let's say we have spectral resolution of del of mu. So we can only resolve photon emitted over the microscopic duration no less than 1 by the spectral resolution. Now the TLS radioactive timeline is way smaller than 1 by del of mu. And so we cannot know what truly happens at this minuscule duration of TLS radiative lifetime. Also, if we look at the two photon absorption and emission, we would require that both of them are like we would require that both of the photons are simultaneously scattered by the atom. But now, if we are using spectral techniques to resolve RF, we are looking at the wave aspect properties of the light, and this undermines the discussion on simultaneity of like the simultaneous emissions of two photons. So yeah, so this thing undermines discussion on simultaneity, which requires photon to be treated as particles. So in this paper, we will propose and experimentally verify a unified model which will simultaneously explain the laser-like line width and also the anti-bunching of the photons. So the main thing in this model is we are considering all RF photons to be spontaneous emissions. So spontaneous emission, as I told, is the emission of a photon when an excited state decays back into a ground state. So yeah, then we theoretically derive the excitation power dependencies measurable at single photon incidence level. So yeah, so here we are not considering that the atom might scatter two photons at a single time. So we will calculate G1 of the RF and G2 of its current component and see whether we get this type of diagram which has the laser light line width and the anti-bunch photons. So all the details, the results here are taken from a theory which was given in an earlier paper. Uh, so before going into the results, I would like to explain the another point. Hello. Now let us start with the supplementary information required for explaining the model um, that we have proposed earlier. So, in theoretical treatment for resonant fluorescence and DLE, it is commonly it is common for the TL and the fluorescent photon to be considered separately, but here we have proposed a pure state model that treats the TLE and fluorescent photon jointly. So let us see how we can do that. For that, we can first define density matrices. Density matrices are basically rho AB, which is rho G0 G0, rho V0 G0 up till rho E0 E0 to E0 E0, where EG are the excited and ground state of the DLE, while 01 are the vacuum and single photon state of resonant fluorescence. Now, if we see what is rho ABCD, rho ABCD is the matrix element for a initial state AB to go into a final state CD. Uh, what does this mean? So this means that if we have a set of initial states and a set of final state in quantum field theory language, there is a probability associated with going from a single state to a final state, and these are all the probabilities that one can imagine exist for our TLE. So like G0 is just means that ground state with no photon emitter going to ground state with no photon emitter. This just means nothing has happened. This means excited state with no photon emitted and excited state with no photon going to excited state with no photon emitted. This is also happening with thing. So these are all the probabilities of all the possible transitions that can happen in an RF. So if we want to have a valid density matrix, we should get rho G0 plus rho G1 plus rho E0 equal to 1. What does this mean? This just means that, so we cannot have E1 because an excited state, if emits a photon, goes to a ground state. So yeah, so we have this TLE. If we just look at TLE, we want the excited state if it's doing nothing, the ground state if it's doing nothing, and the ground state achieved after emission of a photon doing nothing again should add up. All those probabilities should add up to 1, and we have more conditions, which is rho G0 G1 is equal to rho star G1 G0. This is the rule in quantum field theory that if the initial and final state are reversed, their probabilities are the probability is actually the mod square of rho, but the matrix element are actually uh, star of each other. So now if we want reduced density matrix for TLE system, we can write this as so we have to write it in this basis G and E. So we can write it GG, GE, EG plus EE. Now what is the GG matrix? So the thing contributing to GG are G0 G0 and G1 G1. Then the thing contributing for G is G0 and going to E0, and for EJ it's E0 going to G0, and rho AE is rho E0 E0. Here we have the TLE subsystem. Here it is taken out to be separate from the RF, and that's why the RF contributions to the TLE subsystem is not taken into account. That's the reason why we have not everywhere except here, but this just means that the photon is already emitted and then we are looking at the TLE. So similarly, if we look at the reduced density metric for photon, we get 0, 0, 0, 1, 1, 0, 1, 1, where 0, 0 is again G 0, G 0, E 0, E 0, no photon emitted. 0, 1 is G 0 to G 1, one photon emitted in the final state. 1, 0 is rho G 1 in G 0, one photon emitted in initial state, and rho 1, 1 is one photon emitted in initial state going to the one photon emitted in final state. So for the TLE subsystem, the Hamiltonian in the interaction picture can be expressed as this, where omega is the classical Rabi frequency and phi is the phase of the dipole matrix component. What is classical Rabi frequency? So the classical Rabi frequency is, is the probability of transfer of population from ground state to excited state. And we have two operators, which is sigma plus sigma minus, which are the raising and lowering operators of a two-level system. And as the phi has no observable effects in the Hamiltonian, we can choose phi to be pi by 2 and simplify the Hamiltonian to this. After using this Lin-Master equation, we get evolution for reduced matrix for the TLE. Here, these terms are defined to be gamma is 1 by T1, gamma star a spontaneous emission and pure dephasing rate, and dxa rho is other super operators defined as this. So starting with initial state, that initial state of TLE as ground state, the steady state solution for the TLE density matrix is this, where 1 by T2 is gamma by 2 plus gamma star, and we are considering T2 to be less than 2T1. Now let's look at the photon subsystem. In this approximation, B score Bringer approximation, we have the analysis of the Kson operator of photon uh, proportional to the two-level system lowering operator. It just signifies that when excited state comes back to ground state, there is a photon emitted. So after doing that, we have this AT at infinity trace of A of density of P, which is A of density of like the mixed density, which is B sigma minus mixed density, which is B sigma minus reduced density for TLE, which is basically B rho GE, and then we get this. And similarly, a dagger AT at infinity is this. So now if we calculate the G1 at infinity, which is just so it's just A hat T plus tau upon AT hat T plus AT into AT. So we get G1 to be T2 by T1 upon 2 1 plus omega square T1 T2. We can see that G1 infinity goes to 1 when lambda shine goes to 0 and Rabi frequency goes to 0. In the same manner as the earlier, assuming B to be 1 here, because the coherence does not depend on B, we get a reduced density matrix for photon to be less, and also that this photon subsystem is not a pure state but a mixed state. From the reduced density matrix for TLE and photon, we can get the mixed or the joint TLE photon system density matrix using the relation S.2 and S.3, which are given here. Here. So what we get is we get these components, and also the making that the first order coherence can be calculated from rho A and rho B. So from there we also get these components. Then the density matrix looks like this. The only unconstrained components are rho prime E naught G1. So, but we can constrain them through some inequalities. We know that the density matrix should have positive eigenvalues. So let's say uh, rho G1 E naught is from x e to the power iota theta, x being the magnitude is greater than 0. So we have this equation for the eigenvalues of this matrix with A, B, C, D given as such. From here, we can calculate lambda 1 plus lambda 2 plus lambda 3, and then we can obtain the inequalities for all to be positive. From there, we get inequalities between x and t1, t2, and cos theta. We know x is greater than 0, so from here we get t2 cos theta plus this term to be greater than 0, which equals us this. And if the TLA experiences no rephasing, that is, if T2 is to T1, then we get cos square theta equal to 1. There are only two possible theta values, 0 and phi. And if we choose theta to be 0 and x to be 2 sigma square D1, we get our density matrix to be this. From this, we can write the join the pure state psi as root p naught g0 plus root p1 by root 2 e0 plus g1, where p naught is this and p1 is this. Using this solution, we can see that p1 is also equivalent to 2 n star eta ab plus 2 n star eta ab, where n star n bar eta ab is sigma square t1 square is effective average number of photons, and n bar and eta ab are defined in the main text. Using now the Schrodinger filter, we will get one more term here, which is e raised to minus iota 2 pi rho t. Rho is the frequency of driving field. Now I will prove that there are no channel losses. So channel loss is basically when a proton moves from the atom to the detector, it will travel through the medium, and then it might change its state a bit. So whether there is a difference in G1, G2, we have to check that. So let's say a quantum channel, we have a quantum transmission efficiency eta. So the corresponding light annihilation operator xt becomes goes as this, where eta is the transmission coefficient and z of the transmission, and the ZT is the annihilation operator of the reflection part. Then tracing over mod ZT, we can calculate this brackets. So we get xt dagger xt to be eta yt dagger yt, and xt dagger xt dagger xt xt as eta square yt dagger yt yt. So if we calculate G1 tau now, which is xt dagger xt per tau upon xt dagger xt, it just the formula remains the same in YT, and for G2 also the formula in the sense of XT remains in same form in the sense of YT, and so we can say that the channel loss does not affect the analysis of first or second order correlation function. Now let us start the actual calculation of G1 tau and G2 tau. So the first order correlation function and the second order correlation function. So we have this state psi t and its rho naught 0 t gt plus this comes from this state here s.23. So if we take that state and calculate G1 using our coherence definition, so G1 is psi t plus tau psi t a t hat a t plus tau psi t plus tau upon psi t a t hat a t psi of t, which comes out to be t naught e raised to power minus iota 2 pi through tau. And if we calculate the second order correlation function for a zero delay, we get it to be 0. And if g2 of 0 is 0 or close to 0, it just suggests us that the photon has anti-bunching. So yeah, this would be used in the main text for calculations of G2 tau from the data. So let us now look at the origin of Hall's coherence and its partial law. Now I will go a bit fast from here. So, so the main experiments that we do with our coefficients are using AMZI, which is as me. Here you can see the as the picture here. There is this RF coming here. Then we have this 50-50 blue splitter. So that it would add some delay in this path, and the photons will interfere at A and B ports, and at C and D ports we will detect them. This is the simple ASME setup. So as two-path interference occurs between a late temporal mode slightly passing through short arm and an early mode slightly minus tau through the long arm, because the long arm has a delay of tau. So at time t, the t minus tau state would interfere with side t state, which went to the short arm by having no delay. So the joint input state between two temporal modes can be written as the tensor product of psi t minus tau and psi t, which gives us this. Here we can see that this is the zero photon state, this is one photon state, and this is two photon state basically. So here we can see the first term in equation S0 contains one photon, second term contains one photon. Entanglement between two temporal modes, and it produces interference between 1 0 passing to the long arm and 0 to the short arm. This interference 1 0 and 0 1 interference is the origin of RF coherence. Now let's see how we have labeled the poles as ABCD as shown in this figure, ABCD, and this is A prime. If we want to see how the input and output like analysis operators transform into each other, we can write A prime t is equal to half this, and A prime t minus tau is equal to half of this. Then the joint quantum state of port C and D at time t is the interference result of the RF state at times t minus tau and t, which is basically the joint state as written in S.36. After writing A prime t and A prime t minus tau in a normalized form using using 3 dB attenuation, and we know that any attenuation due to channel does not affect G1 and G2 calculations. So to make the calculation easier, we have taken this attenuation to make A prime t and A prime t minus tau simple with respect to dt and ct. So the final state at port C and D comes out to be this. Now this has many terms. The first line contains no photon at C port and D port, while the second and third line represents complementary outputs at port C and D. So this is one photon at C, and this is one photon at D. Also, it contains a phase-dependent term corresponding to TLS transition from G plus CG to GG. So, the remaining terms, which are 1CGE, 1CEG, and 2CGG, these are basically projected into different matter states, and the corresponding transition are from the same EE state to different final state G, E, G, and GG respectively. The first transition, which is E to G and E to EG, correspond to emitting one photon into just one of the two temporal modes, while the last one means emitting one photon to each temporal mode. So it's basically it's basically emitting one photon from here, one photon from here, and they both are interfering at this port. So this would form a photon pair, which and a two photon. So this will form a photon pair, and we will look at this Hong model interference later. So yeah, this is actually the discussion about the input state and the output state of an ASME interference, the ASME setup. Now we will, you know, look at if we consider that the photon are not distinguishable, because till now we were considering that the photon are indistinguishable. If the photon are now not distinguishable, then we have g1 tau to be root of m v naught, which is like m is 1 if it is indistinguishable and m is not like less than 1 if it are distinguishable, where m is defined to be 1 of t minus tau going to t. So yeah, well, where t minus tau going to t means delaying more t minus tau by tau for temporarily overcoming 1t and 1 t minus tau. So yeah. So now I will talk about photon superposition. This is the second phenomenon of which we will look. So photon superposition in the ASME filtered RF. So what is ASME filtered RF? This is this. So we have ASME as this. In filtered ASME filtered RF, we have more ports F and H, and we will look at how photon statistics work at ports F and H. So if we take ASME phi, if we set ASME space to phi equal to pi, in this state we get no contribution from Gg, because 1 plus G is to power iota phi is 0 when phi is equal to pi, and so we are left at D port we are left with only terms 1dGe, 1dEg and 2dGg. So because of this two photon term, we get photon superbunching, which we will see. So let's say we have this HBT setup, and let's say a coincidence event with F detector. So we have a click at F detector at time t1 and at H at time t2. So this involves up to 4 non-degenerate temporal modes, which are coming from T1, T1 minus tau, T2 and T2 minus tau. So let's say all are non-degenerate, which means look at figure number C. So we have nothing overlapping. So T1 is way less than T2 minus tau, and delta T is defined to be T2 minus T1. So let's say if we have all degenerate and we calculate G2, so we get G2 to be 1. Now we will look at the second case when it's doubly degenerate, when T1 equal to T2 basically, and then delta T is 0. And if we calculate if we calculate G2 of 0, we get it to be 1 by P1 square. And so we obtain a superbunching because P1 is less than 1, so we obtain a superbunching at 0 delay. Also, if it's only singly degenerate, so what we need to say is T2 minus tau is equal to T1. So yeah, that just means that the delta T is plus minus tau. So there are only 3 temporal modes. For those 3 temporal modes, we need to define the so for the 3 temporal nodes, we need to calculate dt and dt plus tau, and then if from dt and dt plus tau, we can calculate G2 at phi equal to pi of tau. If we calculate, so first for calculating it, we need to look at the sign. Sign is due to 3 states, and if we calculate the output state equivalent dt plus tau, we get this full expression, and if we put this expression in this G2 tau formula, we get G2 tau to be 1 plus 2b1 over 4b1 squared. And now if we calculate So when P1 is less than 1, and we have 1 plus 2P1 approximately equal to 1, but as the denominator has P1 square, so here also we get G2 as G2 greater than 1, which suggests superbenching. And so the second order interference theorem can be written as this in the limit that P1 is very very less than 1. Now let us talk about phase dependent Mandel interference. So Mendel interferometry is an indispensable tool for evaluating indistinguishability among photons emitted by a single pulsed photon source, as shown in supplementary figure 2b. So 2b. Typical HM interface consists of an ASBA with a path difference of 7 nanoseconds and 2 single photon detectors. The as-match differential deviate tau can be two single photons separated by tau to act temporarily overlap for interference. If perfectly indistinguishable, two photons will coalesce, and therefore the possibility for registering a photon simultaneously at C and D is 0. So let us do the general description of this phenomenon. So let's say quantum light is described by density matrix ρ enters segment to port A and split equally into path A and B, with path A accumulating in phase of and path B at left of the split signal. So here there is this phase of accumulated and there is this phase of tau accumulated. Photons exchanging from port C and D are detected by two single photons. The transmission relation between the output and input light field annihilation operators of the SMA can be given by this, where we have included the loss by first beam splitter. Okay, if we drop the phase e raised to power minus at a 2 pi ρt in equation S.33, so let me show you S.33. So yeah, this is S.33, which is the general pure mixed state for RF fluorescence. Then here we can see that, yes. So here if we write that, we get this in the basis of 0, 1. And now if we take some 3 dB channel loss, we can take phi to be this. And we know that channel loss does not affect G1 and G2. So for convenience and for simple calculation, we can just take phi to be P0 0 plus P1 1 plus P2 2. Because we can have two photons interfering at the beam splitter near C and D. So yeah, let us start now the analysis. Now we have again a coincidence event with C detector clipped at T1 and D at T2. So let's say C clipped at T1, D clipped at T2 involves the input of up to 4 non-degenerate times, again the same scenario as the last section, T1, T1 minus tau, T2 and T2 minus tau, as shown in figure 2C here. Now then again we would have three cases, non-degenerate, singly degenerate and doubly degenerate. So let's start with the non-degenerate case. So then we have the count probability in port C, which is calculated through this formula. It comes out to be this, and at port D it comes out to be this. Here we have ignored the two photon component. So because the two photon component contribution to the total wave function is very less, as P2 is very less than P1 square by 2. And then if we don't have indispensable photons, we have this factor of M coming. So we have corrected PCPD to be this, and then the coincidence probability is this P field times PD, which is like the probability of a count at C and into probability of count at D, then only there would be a coincident event happening in C at C and D, which is this. So they have given a different derivation for calculating this, but I will not go into that. We will just now come to the singly degenerate case. Here also we will have three states, which are t minus tau, t plus tau, and calculating then the c tau, which is pc into pt again. We get c tau to be this, um, and for delta t equal to minus tau, we can do the same derivation and obtain c minus tau equal to plus tau. So we have c plus minus tau is equal to this. And when we have WC degenerate, that is when T1 equal to T2, we have only two states, T1 minus tau and T2 minus tau. So, but now here the we cannot ignore the two photon, because as T1 equal to T2, we can have two photons like, so as these two are on the same magnitude, so this is. So coincidence at this equation are two configurations. One is the multi-photon components in the input and the imperfect two-photon interference. So as these two are on the same magnitude, we cannot ignore now P2 with respect to P1, P0 and P1. And then again calculating the PC and PD, we get C0 to be this. But if we consider finite photon in this interval, we get C0 to be this. This is all the theoretical derivations required for explaining three phenomena of the RF photon. The first one is the anti-bunching of the photon in weak excitation. The second one is the super bunching of in the ASME filtered RF, and the third one is Hong-Mandel interference. All these three phenomena are explained by experiments in our original paper. This original paper here, and all these graphs, the experimental setup, the assumptions which were taken while doing the experiments, how does the graph behave, all these characteristic properties of the graph will be explained by my fellow team members. Thank you.
Alright, so hi everyone, I'm Arya, and in this particular project, I've contributed towards explaining the experimental methods to validate the particular conditions in a lab. So, for testing coherence and resonance fluorescence systems, we basically employ a comprehensive framework for quantum dot based systems. So, to explain a bit of a theoretical background for the same, resonance fluorescence in a two-level quantum emitter, it basically refers to the phenomenon where a two-level quantum emitter interacts with an external driving field, which leads to characteristic fluorescence emission. And in a weakly excited system, RF exhibits two key properties. First is its anti-bunching behavior. So the emitted photons, they basically uh, emit uh, strong quantum correlations, which means two photons are unlikely to be detected simultaneously. And this is quantified by the second order correlation function, which says that g square 0 is less than 0.1. And the second feature is that it has a narrow spectral line width. So the emission spectrum inherits the coherence properties of the driving laser under weak excitation conditions, and a unified theoretical model interprets all emitted photons originating from a spontaneous emission, allowing coherence and spectral properties to be reconciled. So the key equations governing these dynamics are this one. The first one is where G1 T tau is equal to T naught upon 1 plus omega square T1 T2, and this G square 0 is equal to 1 plus 1 minus P naught upon P naught, where P naught represents your ground state population, omega represents your Rabi frequency, and T1 upon T2 represents your excited state lifetime upon dephasing time. Now talking a bit about the core experimental setup. So the core experimental setup, firstly we have to characterize the quantum dots, which are also called QDs. So in the experimental apparatus, a cryogenic confocal microscope is used to maintain temperatures below 4 kelvins. and this is basically done to reduce the phonon-induced decoherence. So you want maximum coherence to be achieved, and for decoherence achieved because of the phonons being present, you maintain temperature below 4 Kelvin. I'm sorry. Then there's also a tunable continuous wave, which is also called a CW laser, which has a wavelength range of 930 to 980 nanometers, and this is primarily serving as your excitation source. So this CW laser is serving as your excitation source. You also have a high resolution spectrometer with a resolving power of delta lambda less than 50 picometers, and it is basically employed to capture fine spectral details. So because you have very fine spectral details to capture in your experiment, you basically use a spectrometer which has a very high resolving power. Some measurement protocols to be kept in mind. The first one being power dependent saturation. To explain that a bit, uh, vary the excitation power from 1 nanowatts to 1 microwatt and record the fluorescence intensity. Then extract the Rabi frequency omega from saturation curves. So when you vary the excitation power from 1 nanowatt to a microwatt and you record the frequency intensity for each of these at different intervals, maybe in a continuous distribution, so you will get a saturation curve, and that saturation curve will essentially give you your Rabi frequency. Determine the excited state lifetime T1 using the time correlated single photon counting. So there's a process called TCS-PC. You can employ that to figure out your uh, time T1, because basically you have a saturation curve and then you have a time correlation with that. So using that curve, you can also extract the omega, which is your Rabi frequency. Then you have spectral diffusion monitoring. So your fluorescence data is collected in 1 millisecond time bends to track spectral fluctuations. And the Allen variance technique quantifies spectral stability and identifies frequency drifts. So your spectral distribution analysis is quite important, and you have to calculate the Allen variance to quantify spectral stability. What exactly is the Allen variance to quantify the spectral stability is quite important in this context. So it is basically also known as a two sample variance, and it is a measure of frequency stability in oscillators, like clocks and amplifiers also. And it is named after David V. Allen and expressed mathematically as sigma square. Just a second. Yeah, it is expressed mathematically as sigma square tau, which basically represents a variance for a two sample variance. And the Allen deviation, which is ADEV, also known as sigma tau, is the square root of the Allen variance. So, a little background of the Allen variance is that by investigating the stability of crystal oscillators and atomic clocks in the earlier times, it was found that they did not have a phase noise consisting only of white noise, but also of flicker frequency noises. And these noise forms become a challenge for traditional statistical tools such as standard deviation, as the estimator is never going to converge. So the noise is therefore raised to be divergent, and early efforts in analyzing the stability included both theoretical analysis as well as practical measurements and pragmatic measurements. So to address these problems, David Allen introduced the M sample variance and indirectly the two sample variance as well. And while the two sample variance did not completely allow all types of noise to be distinguished, it provided a very strong means to meaningfully separate many noise forms with time series of phase of frequency measurements between two or more oscillators. Allen provided a method to convert between any n sample variance to any n sample variance via a two like common two sample variance, and thus making all m sample variances comparable to n sample variances. And this conversion mechanism also proved that m sample variance does not converge for large m, making them less useful. And then IEEE later identified the two sample variance as the preferred measure. So essentially, the change of tau is done by letting it be an integer multiple n of measurement time based tau naught. So tau is essentially equal to n tau naught, where n is any integer. And the interpretation of the value says that an Allen deviation is defined as one half of the time average of the squares of the difference between successive readings of the frequency deviation sampled over sampling period. Now this is all very big words. So it is defined widely for plots conventionally in a log-log format and presentation of numbers. It is preferred as it gives a relative amplitude stability, allowing ease of comparison with other sources of errors as well. And like an Allen deviation of 1.3 into 10 to the power minus 9 at observation time 1 second should be interpreted as there being an instability in frequency between two observations 1 second apart, with a relative root mean square value of 1.3 into 10 to the power minus 9. is what the value of that instability quantified. And for a 10 megahertz clock, this would be equal to 13 microhertz RMS movement, root mean square movement. And if the phase stability of an oscillator is somewhat needed, then the time deviation variance should be consulted and used as well. Moving ahead, talking about the asymmetric Mach-Zehnder interferometer, AMZI. Now the key components here are that the path difference is 10 nanoseconds and it is achieved using a 3-meter optical fiber delay. The phase stabilization, a piezoelectric transducer with a PID controller ensures phase fluctuations that remain below pi by 100 essentially. And your first order coherence measurement, now you have to vary the phase difference pi from 0 to 2 pi. And you have to record interference visibility, which is defined as V equal to I max minus I min upon I max plus I min. And then you have to compare measured visibility to theoretical expectations based on normalized power density. So essentially, your square of your first order coherence has to be somewhat equal to the magnitude of square of your visibility. So there are some validation protocols to be kept in mind. I'll just quickly scroll. So phase dependent two photon interference. The setup for this is that the AMZI is stabilized at phi equal to pi to destructively interfere with laser-like components. And the active path length stabilization ensures that drift remains below lambda upon 100. So whatever is your wavelength, it has to remain less than 100 100th part of that. The procedure says that you'll employ coincidence detection by inducing a time tagging module with 100 picoseconds resolution to record photon arrival times. So every time a photon strikes your sample, you have a photon arrival time. So you'll have it recorded at every time. That's why you have a high resolution, 100 picoseconds resolution time tagging module. And this can acquire over what 10 to the past 6 coincidences per phase setting, which is close to approximately like a million coincidences, which is pretty crazy. Then talking about phase scanning, you step phi from 0 to pi in increments of pi by 20, so you have close to 20 measurements. And then you measure normalized coincidence rate. So basically you'll have your g square for phi phase difference, which will be proportional to 1 minus v into cos phi, where v was your visibility. Now you compare against theoretical values considering photon indistinguishability, because photons are essentially indistinguishable, they're all the same, so there's no distinction there, which is measured at m equal to 0.89. Now there's also a Hanbury-Brown twist setup, which is HBT setup, and this is essentially employed for a second order correlation again. This employs a superconducting nanowire single photon detector, such as SNSPDs, and the coincidence window is approximately 2 nanoseconds, which ensures precise timing resolution. The data analysis here is that you simulate g square delta t using this particular formula, which is given here, this one, and you compare that with the experimental data to verify the anti-bunching. Anti-bunching, as we discussed, is that g square for 0 is less than 0.1. And now here are some error sources and their mitigation. So the first error source is spectral diffusion, which essentially leads to your line width being broadening more than 50 megahertz. And a strategy to mitigate this is that you can use DC Stark tuning to lock your frequency in there. Then there's also the detector dark counts. So artificial coincidences can occur and that can give you like a frequency higher than 100 hertz, which is false. And then Bayesian analysis for error filtering can be employed to mitigate this particular kind of an error. Then we also talk about phase drift, which reduces visibility by approximately 80% at times. And the pound driver Hall lock-in for phase stability is a very good mechanism for mitigating this proper error. Some validation criteria is that like there's a test for your anti-bunching. So when you calculate your g square second order g square 0, it has to be less than 0.1 as a target. The tolerance can be plus minus 0.02. For line width, which is delta mu, it has to be less than 50 megahertz, and the tolerance can be close to plus 5 megahertz, which is essentially we're taking like a 10% sort of an error here. Visibility V has to be greater than 80%, and tolerance can be somewhat close to plus minus 2%. So here's some validation method, and here's some validation metrics as gone through earlier. These are the ones mentioned here as well. Then some advanced techniques. So firstly, there's this technique called squeezed vacuum coupling. So it basically introduces microwave frequency, which is squeezed light, with minus 3.1 decibels of line width reduction, and this detects fluorescence with broadband parametric amplifiers. And the results are that Moller triplet spectrum exhibits phase-sensitive modulation, and coherence validation using T2 equals to 1.62 D1 decay analysis. This is your expected result. Then you also have filtered resonance fluorescence. The setup says that implementing Fabry paired epsilon with 150 megahertz bandwidth. You can use cross-polarized excitation detection to eliminate background light here. And some outcomes are that super bunching, which is the G square is 0. It's not anti-bunching, it's greater than 1.5. At n is greater than 0.6, which is insane. And the time symmetry verification also tells you that the G square for plus tau and G square for minus tau remain exactly the same. So, coming on to the conclusion now, and now for data acquisition and analysis, we stuck to these particular statistical models, which will further be discussed in the coding bit of the videos as well. Talking about the coincidence probability modeling, this is what we essentially used. Now, to quickly conclude what all we discussed right now, this framework presents a detailed methodology for testing coherence in resonance fluorescence, utilizing quantum dot characterization, interferometric phase control, and paving the way for advancements in quantum information processing and photonic technologies. Thank you.
Hello everyone, my name is Harshul and uh, I'm here to present my our work on reproducing the experimental and theoretical results from the paper Coherence and Resonance Fluorescence. My primary contribution to this project have been developing this Python notebook and recreating several plots reported in the paper, and also some simulations and further uh, elucidate the underlying physics. So here is our team. Tanmay and Arya might have already explained the theory and the methods which were in the paper to test the theory in the lab. Uh, Now I'm here to talk a bit about the results. So our primary objective was to create a self-contained analysis framework that reproduces the behavior of resonance fluorescence as described in the paper. And in particular, the paper discusses how a two-level emitter under weak continuous wave excitations exhibits two hallmark features. One is a very narrow laser-like spectral peak, and the other is a strong photon anti-bunching in the autocorrelation measurements. The challenge arises because these two phenomena seem contradictory, and the paper unifies these pictures by treating every fluorescence photon as resulting from a spontaneous emission process in a pure state. So, our goal was to reproduce these experimental observations using theoretical models and validate them by simulating a set of similar plots, which were presented in the publication. And uh, okay, so now I can present the plots. These were the experimental methods, and yep, we start from here. So let's begin with the high resolution RF spectrum plots. In the paper, the authors report a spectrum composed of a very narrow laser like peak with a line width of the order 20 megahertz alongside a broad pedestal corresponding to the natural line width of the emitter, about 2.3 gigahertz. To model this, I developed a function that sums two uh, Lorentzian curves, and the narrow Lorentzian represents the coherent laser-like component, and the broad Lorentzian represents the spontaneous emission from the two-level emitter. And you can have a look at the plot one is a coherent plot of the fraction value of p equal to 0.95. And to simulate a weak excitation regime, the plot faithfully reproduces a spectrum as reported in the paper. Uh, these are a few variations of the same plot, and we also have a combined spectra for in which we have overlaid multiple high resolution RF spectra corresponding to different value of p. You can see it here, and the coherent fraction decreases and the broadband component becomes more prominent, and the multi-curve comparison is a direct reproduction from the paper. Now let's move forward to the first order coherence versus incidence flux. So in this plot, you can see the variation of the first order coherence, which is this given by this equation with the flux included as n bar. According to the theoretical model in paper, we just have to plot this and we get a relation like this. The next plot we made was the fringe visibility versus incidence flux, in which the plot reproduces the relationship between the interference fringe and the incident flux. It is similar to this. And then we plot a combined key parameters versus incident flux in a multi-panel plot, which summarizes the variation of key parameters with incident flux. Uh, we also plotted the filtered second order correlation here, which you can see in the plot. Um, okay, right. And coming forward, we also plotted the autocorrelation for a two-level emitter plot, in which we did a simple approximate code that calculates the theoretical shape for resonance fluorescence under a weak drive, in which we calculated the second order correlation function of an ideal two level atom in a weak drive limit and approximated it as this function. To keep it simple, we produced a lot this sort of shape, and this at least yields anti-bunching near delta t is equal to 0. So let me show you the plot. So this plot serves as a key indicator for quantum nature of this emission. And now we can also plot the detailed comparison of this same plot at different values of the value t, for the value of t. And we plotted it as here. You can see this plot. And for different values uh, of the decay, uh, fast decay represent intrinsic spontaneous emission, and the slow decay with time constant, which is a bit more, represents the coherence of the driving laser. And coming forward, we have also created a simulated plot with theoretical versus simulated data. And finally, we have a plot comparison for second order correlation at zero delay in two cases, without filtering and with filtering. Uh, Finally, we plotted a plot with uh, in the A's AMCI to remove the laser-like fraction, leaving behind the broadband portion, and the portion can be exhibited by super bunching. The predicted formula for the zero decay um, delay second order correlation is given by this, and which can become a huge plot. So let's plot it, which comes out to be something uh, like this. All right. Uh, we also can plot the AMZI interference fringes, where we simulated the interference of fringes between the asymmetric marks and the interferometer. And as you can see, the first order coherence of the emitted light, the interference fringes of the resonance fluorescence have a slightly lower visibility as compared to the laser. Uh, And here I've simulated both the cases to show the difference. The fringe visibility is directly related to the coherent fraction of the emission, and this measurement is very critical for quantifying the first order correlation coefficient. Here we plot the second order correlation coefficient uh, with respect to the incidence flux. Here you can see it. And finally, we have the phase dependent two photon interference. In the paper, as you can also see in the paper, there are interference rates in the experiment of AMZI. It is used to measure the normalized coincidence probabilities as a function of phases. I used fitted parameters provided in the paper for three different excitation flux values to simulate how the coincidence rates vary with the phase. The plot is very crucial as it directly correlates the experimental observations of the interference in the two photon regime. And here are the plots. And this is something else we did, which is for photon counting histogram. This plots basically simulates a histogram using a Poisson process, which reflects the inherent photon statistics of the source. We compare the simulated data with the theoretical Poisson distribution. Why? So while this is not directly reported in the paper, it serves as an important validation of the statistical nature of light. And final discussion. Um, in summary, we have uh, successfully shown the results of the paper, and uh, that's all. Thank you so much.